Welcome to AWS Mastery Labs, turning AWS chaos into clarity with bite-sized tutorials, hands-on labs, and exam-smashing tips. In this video, we'll explore how to containerize your applications using Docker and seamlessly integrate them with Amazon Elastic Container Registry, AWS's fully managed container image repository. We'll start by introducing the core concepts of Docker, images, containers, and the benefits of containerization in modern DevOps workflows, and then discuss the benefits of having Amazon ECR to securely manage and version your images in the cloud. Let's get started. At its core, a container is a lightweight, standalone executable package that includes everything needed to run a piece of software: code, runtime, system tools, libraries, and settings. This self-contained approach ensures that the application behaves the same, regardless of where it's run, whether it's on a developer's laptop, in staging, or in production in the cloud. Containers are built from Docker images, which are composed of layers stacked on top of each other. Each layer represents a set of file system changes, like installing a package or copying source code. This layering makes image builds efficient and encourages reuse across multiple projects. One of the biggest advantages of containers is portability. By packaging all dependencies with the application, containers eliminate the classic "it works on my machine" problem. This makes them ideal for microservices, CI/CD pipelines, and hybrid cloud environments. Containers also offer process and file system isolation, which means each container operates in its own space, reducing the risk of interference or unexpected behavior from other containers running on the same host. They are also incredibly fast to start, often in just a few seconds. Using a Docker file, we can define how an image is built using code. This makes the entire build process support versioning, testing, and automation, bringing containers right into the DevOps and infrastructure as code ecosystem. By design, containers are typically stateless and ephemeral. That is, they don't retain data after being stopped or restarted. This encourages the use of external services for persistence, making your application architecture cleaner and more modular. Finally, containers are the building blocks of powerful orchestration platforms like Amazon ECS, EKS, and Kubernetes, which allow you to automate deployment, scaling, and management of containerized workloads at scale. To really understand the power of containers, it's helpful to compare them with traditional virtual machines, or VMs. Let's start with architecture. Virtual machines run on top of a hypervisor and include a full guest operating system, along with virtualized hardware. This means each VM carries its own OS image, making it relatively heavy. Containers, on the other hand, share the host operating system kernel and isolate applications at the process level. This makes containers significantly more lightweight and faster to start. Because containers don't need to boot an entire OS, they can start in seconds, sometimes even milliseconds, whereas VMs might take minutes to come online. This responsiveness is a game changer for auto-scaling and rapid deployment scenarios. When it comes to resource efficiency, containers have a clear edge. They require less CPU and memory overhead, which allows for higher density on the same host. You can run many more containers than VMs on a given machine, optimizing your infrastructure costs. Now let's talk about isolation. VMs provide strong isolation with dedicated OS environments, making them ideal for workloads that require strict security or kernel-level customization. Containers provide process-level isolation using technologies like namespaces and control groups, which is generally sufficient for most cloud-native applications, though not as airtight as VMs for some high-security use cases. Portability is another key differentiator. Containers encapsulate all dependencies within a single image, making them easy to move across development, test, and production environments on any platform that supports containers. VMs, by contrast, are often tied to specific hypervisors or operating systems, making migration more complex. Persistence also differs. Containers are typically ephemeral and stateless by design, well suited for microservices and scalable web apps. VMs with virtual disks and persistent file systems are better for monolithic applications that expect to retain state locally. In summary, containers are ideal for modern, scalable, cloud-native applications where speed, efficiency, and portability are key. VMs still hold their place for workloads that demand full OS environments, legacy support, or strict isolation. Docker is a platform that fundamentally changes how we build, ship, and run applications. It introduces a consistent way to package software so that it runs reliably across different environments, from a developer's laptop to staging and production in the cloud. At its core, Docker provides a standard approach to containerization, and it's largely responsible for making containers a mainstream technology. By wrapping applications and their dependencies into a single, portable unit, Docker allows teams to move faster and deploy with greater confidence. One of Docker's biggest advantages is how well it enables DevOps practices. Developers can build, test, and ship containers, while operations teams can deploy and monitor them using the same artifacts. This reduces friction between teams and supports rapid, iterative workflows, all the way through automated deployment pipelines. Docker also plays a pivotal role in the shift toward microservices architecture. Instead of deploying one large monolithic application, you can break your system into smaller modular services, each running in its own container. This makes it easier to scale, maintain, and evolve different parts of your system independently. Another key strength of Docker is its cloud-native readiness. It integrates seamlessly with cloud platforms like AWS, Azure, and Google Cloud, and serves as the foundation for orchestrators like Kubernetes and Amazon ECS. Whether you're deploying on a local server or across a multi-region cloud infrastructure, Docker gives you the flexibility to deliver applications consistently at scale. Finally, Docker benefits from a thriving ecosystem and community. From pre-built images to plugins, tools, and best practices, there's a rich set of resources available that makes Docker highly extensible and easy to adopt, regardless of where you are in your container journey. Now that we've introduced Docker as a containerization platform, let's take a closer look at its core components, the building blocks that make Docker so powerful and easy to use. We'll start with Docker Engine. This is the heart of the Docker platform. It's a lightweight runtime and daemon that enables you to build and run containers. It handles tasks like image management, container lifecycle, and network communication under the hood. Next, we have Docker images. Think of an image as a blueprint for a container. It includes everything your application needs to run: the code, system libraries, runtime, and any dependencies. Images are built once and can be reused across environments, ensuring consistency between development, testing, and production. Once you have an image, you can run it as a Docker container. A container is the live, executable instance of that image. It runs in an isolated environment on the host system, using the shared OS kernel. Containers are lightweight, fast to launch, and perfect for scaling services up and down as needed. Then there's the Docker file. This is a simple text file containing a set of instructions used to build a Docker image. It defines how the image is created, from specifying a base image to installing dependencies, copying source code, and setting environment variables. Managing all of this is easy thanks to the Docker CLI and API. The Docker command line interface lets you interact with the Docker engine to build images, start or stop containers, manage networks, and much more. For automation and integration, Docker also exposes a RESTful API, which makes it highly scriptable and compatible with CI/CD pipelines. Finally, we have Docker registries. These are centralized repositories where Docker images are stored and shared. Docker Hub is the public registry, but you can also use private registries or cloud-native options like Amazon ECR to control access and manage image versions securely. Let's walk through the Docker execution environment and explore how the Docker components interact to build, store, and run containers. On the left, we begin with the Docker client, which is the primary interface users interact with. Whether you're building a new image, starting a container, or pulling from a remote registry, all of it starts here. Common commands like docker build, docker pull, docker push, and docker run are issued from the client. These commands communicate with the Docker daemon on the host machine via REST APIs. At the center of this environment is the Docker host. This is where the Docker daemon, a long-running background process, lives. The daemon is the heart of Docker's architecture. It handles image management, container lifecycle, and interaction with external registries. The Docker daemon manages two core components: images and containers. Images are the blueprints. immutable templates that define the container's runtime environment. When you run a container, it's essentially a live instance of an image. The illustration shows multiple images stored locally and several active containers running side by side, each isolated and self-contained. On the right, we see the Docker registry. This is where images live when they're not on your host. It can be a public registry like Docker Hub or a private one like Amazon ECR. The Docker daemon communicates with the registry over secure REST APIs. Let's look at the interaction flow. When you use Docker build, the client sends the request to the daemon, which constructs the image and stores it locally. A Docker pull command retrieves an image from the registry. The daemon downloads it and saves it to the local image store. Conversely, Docker push uploads your image from the host to the registry, making it accessible to other environments or teams. And with Docker run, the client asks the daemon to spin up a new container from a specified image. The daemon takes care of creating, starting, and managing that container's lifecycle. This architecture allows Docker to remain lightweight, flexible, and consistent, making it the go-to solution for containerization across local development and cloud deployments alike. Let's walk through some key recommendations that will help you produce production-ready images. First, use minimal base images whenever possible. Images like Alpine or Google's Distroless are small, fast, and carry fewer vulnerabilities than heavier distributions like Ubuntu. This reduces your attack surface and makes builds more efficient. Next, adopt multi-stage builds in your Docker file. This approach lets you separate your build environment from your runtime environment. You can compile your code or run tests in the first stage and copy only the necessary artifacts into a clean, minimal final image. The result is a smaller, more secure image that contains only what's needed to run your application. Another important best practice is to tag images explicitly using version numbers or build identifiers. Avoid relying on the latest tag in production. It can lead to inconsistencies across environments and make it difficult to trace which version of your app is running. It's also critical to keep secrets out of your images. Hard-coding credentials or API keys in Docker files or images is a major security risk. Instead, use secure environment variable injection, cloud-native secrets managers, or orchestration layer secrets handling. When writing your Docker file, optimize the order of your instructions to maximize layer caching. Place frequently changing commands like copy and run statements that rely on source code changes near the bottom of the Docker file. This allows Docker to reuse unchanged layers and speed up rebuilds. Always use a .docker ignore file to keep unnecessary files out of the build context. They slow down builds and bloat image size unnecessarily. Lastly, for security, run containers as a non-root user. By default, containers run as root inside the container, which can be a serious security concern. Adding a dedicated user with limited privileges reduces the impact of any potential compromise. Managing Docker containers in the cloud becomes significantly more streamlined and scalable with AWS's suite of purpose-built services. Let's start with Amazon ECS, or Elastic Container Service. ECS is a fully managed container orchestration platform that simplifies the process of deploying, managing, and scaling containerized applications. It's designed with deep AWS integration and is ideal for teams looking to stay within the AWS ecosystem. Next, we have Amazon EKS, or Elastic Kubernetes Service. If your team is already using Kubernetes or needs Kubernetes-specific tooling and open-source compatibility, EKS delivers. It provides a managed control plane, automatic upgrades, and security patches, so you don't need to worry about the heavy lifting of running your own Kubernetes clusters. Now let's talk about AWS Fargate, which is the serverless compute engine that powers both ECS and EKS. Fargate eliminates the need to provision and manage servers altogether. Instead, you simply define your container requirements, such as CPU, memory, and networking, and Fargate handles the infrastructure behind the scenes. Finally, there's Amazon ECR, or Elastic Container Registry. ECR is a fully managed Docker container registry that makes storing, versioning, and deploying container images secure and seamless. It integrates natively with ECS, EKS, and Fargate, ensuring that your container lifecycle is tightly coupled with AWS best practices. Together, these services form a cohesive and powerful platform for Docker container management on AWS. allowing teams to deploy with confidence, scale effortlessly, and maintain high operational efficiency. Amazon ECR is a fully managed container registry service that allows you to securely store, share, and deploy Docker container images. With ECR, there's no need to operate your own container registry or worry about scaling the underlying infrastructure. ECR is tightly integrated with the broader AWS ecosystem. Whether you're using Amazon ECS, EKS, AWS Lambda, or Code Pipeline, ECR fits seamlessly into your CI/CD and container orchestration workflows. This makes it easy to automate deployments and streamline your software delivery pipeline. One of ECR's key strengths is high availability and scalability. Built on top of AWS's robust infrastructure, ECR offers regional redundancy, low latency access, and the ability to support high throughput image pulls and pushes, making it suitable for everything from small dev teams to enterprise scale workloads. Security is also a first-class concern. With image scanning built in, ECR can automatically scan your container images for known vulnerabilities using Amazon Inspector. This allows teams to catch and remediate security issues early in the development cycle, before images are ever deployed to production. To help manage storage over time, ECR provides tag immutability and lifecycle policies. Immutability ensures that once an image is tagged, it cannot be overwritten, helping preserve version integrity. Lifecycle policies automatically clean up older or unused images, reducing clutter and saving on storage costs. ECR supports both private and public repositories. You can use private repositories for your organization's internal workloads, or publish images to public repositories if you want to share your tools or base images with the community. Finally, ECR is optimized for performance. It leverages Amazon S3 under the hood for durable, highly available storage, and it delivers fast, secure transfers over HTTPS, making image pulls and pushes efficient and reliable. When choosing a container registry, it's important to understand how different options stack up against each other. Let's compare Amazon Elastic Container Registry ECR with two other popular choices, Docker Hub and GitHub Container Registry GHCR. Amazon ECR is deeply integrated into the AWS ecosystem. It's designed to work seamlessly with services like ECS, EKS, Lambda, and Code Pipeline. This native integration streamlines authentication, orchestration, and automated deployments. In contrast, Docker Hub and GHCR are more cloud-agnostic, often requiring custom scripts or third-party tools for integration into cloud platforms. Each registry service implements its own authentication mechanism, tailored to its architecture. Security is another key differentiator. ECR offers built-in image vulnerability scanning, powered by Amazon Inspector, enabling security checks as part of your pipeline. Docker Hub offers image scanning too, but only on paid plans. GHCR includes vulnerability advisories integrated with GitHub Dependabot, helping you catch issues directly in the GitHub UI. Private repository support varies as well. ECR provides unlimited private repositories by default. Docker Hub offers private repos but restricts usage under its free tier, including rate limits for unauthenticated pulls. GHCR allows private repositories with access managed through GitHub's familiar team and org structure. In terms of image management, ECR supports tag immutability and lifecycle policies, which help you enforce version consistency and automatically clean up old images. Docker Hub and GHCR offer these capabilities manually, often requiring custom scripts or external tools. Finally, ECR is optimized for performance. It's backed by Amazon S3, delivering high availability and fast image transfers within the AWS network. While Docker Hub and GHCR are performant, their speeds can vary depending on region, load, and connectivity. In short, Amazon ECR is the best fit when you're building containerized applications inside AWS. Docker Hub is ideal for broader community sharing and simple workflows, while GHCR excels if your code and CI/CD processes live primarily within GitHub. Managing container images effectively is crucial for maintaining a clean, secure, and scalable container ecosystem. And Amazon Elastic Container Registry, or ECR, provides robust tools to do just that. First, organizing repositories is key. In ECR, you can create multiple repositories to logically group your images by application, team, microservice, or deployment environment. This gives your architecture clarity and makes it easier to apply policies, monitor usage, and control access at a granular level. Next, There's tagging strategy, a vital part of image management. You can assign meaningful tags to each image, such as semantic versions like 2.3.1 or environment-specific labels like dev, staging, and prod. This enables clean image promotion workflows and allows developers and deployment tools to reference the right version every time. To ensure consistency and prevent accidental overwrites, ECR supports image tag immutability. When enabled, this feature blocks any push that tries to overwrite an existing image tag, preserving the integrity of version deployments and making rollbacks more reliable. Over time, registries can fill up with outdated or unused images. That's where lifecycle policies come in. These allow you to define automatic rules to clean up stale images, like removing untagged ones older than 30 days or keeping only the last 10 versions. This helps optimize storage usage and reduce costs without manual intervention. ECR also integrates seamlessly with the AWS CLI and SDKs, making it easy to authenticate and perform operations like image pushes and pulls directly from your pipelines. Finally, if you're operating across regions or accounts, ECR's cross-region and cross-account replication lets you automate image distribution where it's needed, helping you meet performance, redundancy, and compliance requirements. Modern DevOps workflows rely heavily on seamless, automated pipelines, and Docker combined with Amazon ECR fits right into that ecosystem, empowering teams to build, test, store, and deploy containerized applications with confidence and speed. In a typical CI/CD flow, everything begins in the continuous integration CI phase. Here, tools like AWS Code Build, GitHub Actions, Jenkins, or GitLab CI are triggered by code changes, such as a commit to the main branch. These tools automatically build a Docker image from the updated codebase, encapsulating all dependencies and environment configurations. Once built, the image is tagged intelligently, using semantic versions, git commit shays, or labels like dev, staging, or prod. These tags serve as immutable references that help you promote images consistently across environments without rebuilding. After a successful build and test cycle, the CI pipeline pushes the image to Amazon Elastic Container Registry, ECR. This push step makes the image available in a secure, scalable, and regionally optimized repository. ECR handles storage and versioning and serves as the source of truth for all downstream deployments. In the continuous deployment CD phase, services like AWS Code Deploy, ECS, or EKS pull the required image directly from ECR. This enables fast and consistent deployments across environments, whether it's a dev cluster, a staging environment, or production. Thanks to immutable image tags, teams can quickly roll back by simply redeploying a previously known good image version without needing to rebuild or reconfigure the application. To enhance governance, repository-level access controls in ECR allow teams to enforce strict boundaries between environments. This architecture not only increases delivery velocity, but also strengthens reliability, traceability, and consistency across your deployment lifecycle. Amazon ECR delivers a range of features designed to protect your software supply chain and help meet regulatory and operational standards. To begin with, ECR repositories are private by default. This means that unless explicitly configured otherwise, your images are not accessible to anyone outside your AWS account. This default posture ensures a strong baseline for image security. Access control is highly customizable. With fine-grained IAM policies and resource-based access policies, you can define who can push, pull, or manage specific repositories. This gives you full control over who touches what, across teams, services, or even accounts. When it comes to protecting your image data, ECR encrypts all images at rest. You can use AWS managed keys or opt for customer managed keys via KMS for more granular control and auditability. In addition, all communication to and from ECR is encrypted in transit using HTTPS, safeguarding your data against interception during image transfers. To further strengthen governance, ECR supports tag immutability. By enforcing immutability, you prevent accidental or unauthorized overwrites of image tags, ensuring version integrity and simplifying rollback procedures. Auditability is another key area. Every interaction with ECR, from pushes to pulls, is recorded via AWS CloudTrail, giving you a detailed log of actions for security audits, incident investigations, and compliance tracking. Together, these capabilities ensure that your container image infrastructure is secure, controlled, and fully auditable. laying the groundwork for safe and compliant containerized deployments across your organization. ECR uses a straightforward pay-as-you-go pricing model that primarily revolves around storage usage. You're billed based on the total size of your container images stored in the registry, measured per gigabyte per month. There are no upfront fees or minimum commitments, making it flexible for teams of any size. For smaller teams, proof of concept projects, or developers just getting started, ECR includes a free tier, offering 500 megabytes of storage per month for private repositories for the first 12 months. This is a great way to explore the service before incurring charges. Pulling images within the same AWS region is free, which means that deploying containers to ECS, EKS, or other services in the same region incurs no additional transfer cost. However, if you pull images across regions, standard AWS data transfer fees apply, so architecting for regional proximity can yield savings. There are no extra charges for common registry operations like Docker pull, Docker push, or listing images. All API requests to ECR are included in the base pricing, so you don't have to worry about being billed per interaction. To keep costs under control, ECR supports lifecycle policies that can automatically delete untagged or outdated images. This feature helps eliminate unnecessary storage usage, especially in active CI/CD environments where new images are built frequently. It's worth noting that public repositories in ECR are free to use, with generous limits on both storage and data transfer. This is particularly beneficial for open source projects or publicly shared images. Additionally, optimized image management, such as minimizing image layer sizes and removing unused dependencies, can significantly reduce both storage and transfer costs over time. Let's look at some strategies that can significantly reduce your bill while keeping your workflows efficient and secure. First, consider enabling image tag immutability. By preventing overwrites of existing tags, you avoid redundant storage of similar image versions, ensuring that only truly unique builds occupy space in your registry. Next, take full advantage of lifecycle policies. These allow you to automatically clean up untagged or outdated images after a specific time or threshold, and is one of the most effective ways to trim storage costs without manual cleanup. Optimizing the size of your images is another high-impact practice. Use minimal base images like Alpine, remove unnecessary dependencies, and clean up temporary files in your Docker file. Compressing image layers can also help. Well-structured, reusable layers that are compact lead to more efficient caching and reduced image pull size, saving both time and bandwidth. To avoid unnecessary charges, be mindful of cross-region image pulls. Always pull from ECR repositories in the same region as your workloads whenever possible. If you're working on dev or test workloads, leverage the free tier. With 500 megabytes of free private storage per month for the first 12 months, it's perfect for experimentation and early-stage development. Organizing your repositories with clear scoping, such as separate repositories for dev, staging, and prod, gives you more control over retention policies and helps prevent cost leakage. Lastly, stay informed. Use AWS Cost Explorer and budgets to monitor your usage, set alerts, and forecast costs based on historical trends. This visibility lets you course correct before costs become a problem. With Amazon ECR, AWS provides several built-in tools that make it easy to track repository usage, detect anomalies, and automate responses, all of which help maintain the health, security, and cost efficiency of your container ecosystem. First, Amazon CloudWatch Metrics gives you a window into ECR's operational activity. You can monitor metrics such as the number of image pulls and pushes, repository size, and API call counts. These metrics are invaluable for spotting trends in usage, understanding how your image repositories are growing, and identifying any unexpected behavior. AWS CloudTrail adds a powerful layer of auditability. It records all API calls made to ECR, including who accessed a repository, when they did it, and what action they performed. Whether it's pushing a new image, pulling an existing one, or deleting a tag. For more dynamic workflows, Amazon EventBridge comes into play. ECR emits events such as image pushes and vulnerability scan completions. These events can trigger automated downstream actions. Another key monitoring feature is lifecycle policy evaluation logs. When you apply lifecycle policies to your repositories, ECR generates logs showing which images were marked for deletion and why. This transparency ensures that automated cleanup doesn't come at the cost of unexpected data loss. If you've enabled image scanning, ECR provides scan findings that highlight known vulnerabilities in your container images. These results can be viewed directly in the console or accessed via the API, giving developers and security teams insight into the security posture of every image before it's deployed. Finally, you can create custom dashboards using CloudWatch to visualize all this data in one place. These dashboards provide a centralized and actionable view of your ECR usage, empowering proactive decision-making. Thank you for joining us in this video. If you haven't already, we'd love for you to subscribe to our channel to stay updated with our latest content. We look forward to sharing more insights with you in another video. Until then, keep exploring. And thank you for watching.